Good morning, everyone. How did the homework go? Any questions from the homework? Amelia? Okay. Anybody else? I'll give you a minute or so to get your notes, whatever, back to all together. Okay. Now we start looking at number 43. Very good. Number 43. Okay. Emptying a water trough. Okay, a cattle trough has a trapezoidal cross section with a height of 1 meter and horizontal sides of length 1/2 of a meter and 1 meter. So we'll draw the picture in a second. Assume the length of the trough is 10 meters. How much work is required to pump the water out of the trough to the level of the top of the trough when it is full? And if the length is doubled, is the required work double explained? Okay, so let us do part A. So we have the following picture. So I'm going to draw it. So we have a trapezoid here. So this goes like that. And this is my picture. And then we have the same thing here. Yeah, I can hear this noise. I'm going to start. Okay. Yeah. So very good. So it's going to go like this. Okay, so that's my picture. Okay. Now we have some dimensions. So the dimensions are from here to here, the height from here to here is a height, not the length of the side. So that's 1 meter. From here to here, we have 0.5 meter. And what else? And from here to here, we have 1 meter. So these are the dimensions. And it's full of water all the way to the top, absolutely full. And it's 10 meters here. Okay. And you want to pull all the water out. And you have to find the work required to do that. So as we said yesterday, the water on the top, the water on the bottom need different amount of work to be lifted because they are at a different distance. So to be able to do that, we would divide the water inside the trough into layers, and we think layer by layer. We think layer by layer. Now to do that, first we have to introduce like a reference, a zero and an axis. So a good place to pick a zero is right in the middle. So we use our really best intuition to do that. And the positive x-axis go up the way the direction of motion. So we pick our axis straight in the middle. And then we have to take a layer. So we fix a height, yi. So we have yi unit above the base. And we take a layer. So a layer. And we focus on this one layer. So this is my layer. Right there. So this is my layer. And remember, it has a thickness. That's my delta y. So, and this is my layer right here. Sorry. Okay, so that's a layer. And that's it. So there's a certain thickness attached to it. Okay. And now we focus on this layer. And we ask ourselves, how? So this is my typical layer. Okay. And the height of this layer is my delta y. So my delta y is from here to here. That's the height of the layer. And I focus on this particular one. And I ask myself, okay, what's the work needed to lift this particular one? So the question is, The idea is we divide the water horizontally into layers of height delta y. Delta y, okay? Now, what's the shape of the layer? Yesterday, when we did the problem, most of the time, the shape of the layer were a cylinder. What's the shape of a layer here?
Rectangle.
Is a rectangle, not quite a rectangle, because we have a height, delta y, to it. So it's not like a flat object.
Rectangular prism.
Exactly, it's a rectangular prism. Okay, so now the question, we have to find the work done on each layer. So that's what we have to do. So work done on each layer is equal to the distance by which a layer is lifted times the weight of the layer, or the force by which a layer should be lifted. All right, so first we're going to do them one by one. First, what's the distance? Remember, each layer is yi meter above the base. That's the way. So the first layer is on the base. The second is yi unit above it, y2 unit. So the layer is really above the base, yi unit. So it means that from here to here, this is my yi. So we have to understand the picture, otherwise nothing makes sense. Now, question back to you. By what distance is each layer lifted by? So now you focus on this. Forget about everything. You have one piece, this rectangular prism, this big chunk of water. And within this chunk, because delta y is small, all the water will be lifted by the same distance. By how much? Okay, 1 minus the yi. Absolutely correct. So the distance is 1 minus the yi. Okay. Now the weight of the layer. So this is a layer of water. Weight is the volume of the water times the density. Volume of the water, or actually in this case, is the density of water times the volume of the prism, of the rectangular prism. I'll write it clearer. Okay. All right. The density, did they give us the density? No, usually it's 62.4. So I don't know if they expect you to enter density in MATLAB or 62.4. I forgot that. So that's the density. So let me call rho the density, because that's usually the letter used for density. So we're going to use the letter rho to stand for density. So we're going to call this a rho times the volume of the prism. And that's what we have to go back to the picture. And this is really where the change from yesterday will occur. So what's the volume of a prism? Back to you. So that's the prism. So what's its volume in general? So if you have a little box here, so we have really a box here. We just have a box. This layer is nothing more than a box, something like that.
Length times width times height.
Right. So it's length times the width times the height. So this is not a good picture. The length here is 10 from here to here. The height is the delta y. And then we have the width. And now here's the question about the width. Is the width constant, or the width changes with how high we are above the base? The width in my picture is from here to here. That's the width. We're going to call it wi. And my question to you is the width changing as we go up, or the width is constant? Quick question.
Changing.
Changes. The higher we are, the bigger the width is. The higher we are, the bigger the width is. So now the question is, can I express the width in terms of the height? So to be able to solve the problem, y is going to be my only variable. Everything else have to be expressed in terms of y. So the volume of the prism is the length times the width times the height, which is my delta y. Okay, rho is the density, so we keep it. The length in this particular case is 10. The width is my big issue, I keep it open. And the height is my delta y. So now my whole problem is to express the width in terms of the height above the base, because it's definitely changing with the height. Okay. And to do that, that's really our main issue. So it's more of a geometrical issue than anything else. So now we're gonna take a picture here, a nice piece of paper, and you're gonna find the W. So to find it, I'm gonna take this piece here, what I call this trapezoidal cross section, and I'm gonna draw it right here and work with it so we can find the width. So it's going like that, and this is the 0.5 here. So now I'm gonna isolate this issue to find the WI. So this is my piece. So this cross section, that's really what I'm copying here. My 0 right there, so that's my axis. That's my 0. And from here to here, that was the 0.5. From here to here, it's 1 meter. And from here to here is 1 meter. Okay. And we are going to do this problem actually in 2 different ways. We're going to do it geometrically, and then we're going to do it algebraically. And my layer was right there. Okay, so this is my layer. This is from here to here. That's the yi. And I need to find this piece. Okay, so that's my wi. All right, who has any idea? Anybody was able to do it? As I said, we will be doing it in 2 ways, geometrically first, and then we'll do it algebraically. Okay, who has any idea how to do it geometrically?
There are 2 triangles on either side. So I just tried to figure out the proportions.
Which triangle? I don't have triangle right now, right?
Right, so you take the rectangle out of the middle, and then there's 2 triangles on either side.
Ah.
Yeah.
Okay. Now the other is symmetric, so let me worry about this piece.
Right, okay.
Right? So he drew the triangle. Now what's the benefit of what he's doing? From here to here, how much do we have quickly? So we're doing it purely in a geometrical approach. From here, so this is my yi here. How much do we have from here to here? All of you.
0.25.
What? Repeat.
Is it 0.25?
Absolutely. It's 0.25. Because this whole down length is 0.5. So with this halfway is 0.25. So this piece is very easy. So the real problem is this one from here to here. And that's when your classmate is telling me you similar triangle. So let me call this like a little bit like Li. And so this is Li, these are my triangle. Okay, how much I have from the top? This little red thing. So that's the triangle I'm going to focus on. That's the triangle. Okay, so we have Li divided by equal to the big triangle and the little one down here. So let me give them names. A, B, C, D, E. Okay, I don't have to give them name, but just to make the picture clear. So the triangle ACD, that's the big one, is similar, ACD is into the triangle BCD. This is the similarity I am working with. Okay, so now let us take the similarity. Li divided by, from here to here, AE. How much is AE? Just use the picture.
0.5.
Point how much?
0.25.
0.25, because this whole thing is 1 meter. This is from here to here is 0.25 because that's a rectangle. So I'm left with 0.25. So I'll equal to, remember, it's the big triangle and the little one. Yi, because that's how much I have from here to here, divided by 1. So this will give me that Li is basically 0.25 Yi. It means Li is 1/4 of Yi. Okay, so now what is my width? My width is the whole thing. That's Wi. That's Wi. So Wi is going to be 2 times 0.25 plus Li. Twice because twice. It's from here to here. So it's 2 times 0.25 plus 1/4 Yi. So this is going to be equal 1/2 plus 1/2 Yi. And that's the Wi. Okay. So that's really, it was the hardest part. Now let's put the picture together, and then I'll go back and do that analytically. So we solved this problem purely in geometrical way, then we're going to do it analytically after that. But first, I would like to finish the problem. Okay. Then let's go back to my picture and put the whole thing together. So now that's the weight. It's the density times 10 times the width. The width is 1/2 plus 1/2 Yi. And now finally, we are going to put the problem. I find the work done on each layer. I found the distance that by which a layer is to be lifted, and I found the force by which a layer has to be lifted by, which is only the weight of it. So work done on a layer. Okay, so now let's go back and do that. So work done on a layer. On one layer is equal to the distance times the force. Times the delta y. Now the work done on the whole body of water is the sum of the work done on every layer. So now the total work is the sum, sigma, of the work done on each layer. And as I told you a lot of time in physics, this expression is called elements of work. Okay. All right, so now we turn this into an integral, because as delta y becomes smaller and smaller, then saying that the distance is 1 minus y, I become a more and a more and a more accurate way of doing this. So the work will become, we just have to integrate all those. So it's 1 minus y times the density times 10 times 1/2 plus 1/2 y dy. And always my limit. To catch all the water, we have to divide the interval from 0 to 1 because my trough is full to the top. Finally, we have to integrate. So the only way to integrate, we have to take the constant out. So I'm going to take 10 rho out. And then I will be left with 1 minus y. Actually, I can even take this half out because it's a factor. So I don't have to work with it. And then I will be left with 1 plus y dy. Okay, and the rest is relatively simple. So this will give me 10. So this gives me 5 rho integral from 0 to 1. And now I just multiply out. I will get 1 minus y squared dy. And then the rest is up to you to finish it, which is simple. And the unit, it depends on rho, but since the y is in meter, So I'm assuming here the unit is going to be in joule. Okay.
So that row, do we have to like multiply it back in at the end?
Usually I will give you the density of the water. I don't know if MATLAB is giving you the density. I did not check that. Do you guys know whether MATLAB give it to you or not? Anybody knows? Anybody who did the homework? No.
I think it usually does, yeah.
They
Yes,
They'll
it does.
give you the densities and acceleration.
Okay, so if they give you the density, then the density should be 62.4.
Oh, it's usually, I think like on each problem it was like 1,000 or something.
Ah, okay. If it's 1,000, yes. If it is 1,000, that's in kilograms per meter cube. Then you have to multiply it by 9.8 to get it in Newton. Are you with me? Well, so
Yeah.
the rho, if they give it to you in kilograms, so if they tell you it's 1,000 kilogram, we did that yesterday per meter cube. That's a unit of mass. Okay, so what you have to do is to take the 1,000, you times it with 10.8 to get a unit of weight. And by doing this, then the unit will be Newton per meter cube. Okay, that's how you handle the MATLAB. All right, so since I should have looked at that, I didn't pay attention whether they give it to you or not. So that's how you do it. So it's 1,000, you multiply it by 9.8, and then you have to multiply it out to get the last answer. Okay. Any questions? All right, so as I promised you, I would like to take this piece again, this piece of the problem, and do it in an analytical way that I think you guys should be familiar with. So, okay, so what I'm going to do, how to find WI. The question is how to find, another way to find WI. How to find WI analytically or algebraically if you want, not geometrically. So that's the only piece I'm going to really work on. All right, so I'm going to draw my picture again. So okay, that's my picture. That's my 0. And that's my y-axis. Okay. And this is my y right here. And I needed the distance from here to here, which is, as we did in the previous problem, it's enough to find this distance, this horizontal distance. So this is my yi here. If I find this horizontal distance, it's enough. I multiply it by 2 and I get the whole thing. So basically, I can think of it as the following problem. I'm going to introduce an x-axis. I'm going to call this x-axis. Okay? And the idea that if I know the equation of this line, so that's a line. Okay? If I know the equation of this line, it means that if I know the y, I will be able to find the x. So something we did a little bit previously. So what we're going to do in this approach is find the equation of this line. It means find the relationship basically between the x and y coordinate of every point. In such a way that if I have the y, the equation will give me the x, which is exactly what I want. Okay, so we're going to find the equation of the line. To find the equation of the line, we need 2 points on the line. So let us see the 2 points. This point, that was the 1/4 or 0.25, it's a 0. And this point up here, because from here to here, we had 1 meter. So this point up here will have to be 1 for y, because from here to here also we have 1 meter. So 1 for y, and this is going to be a 1/2 or 0.5. So now we're going to find, so we're going to call this line L. So let's find the equation of, let me call this line L. We're going to find the equation of L. Okay, so we need the slope. Now it's going to be the slope, change of y over the change in x. So this is going to give me -1 over -1/4. This is going to give me a 4. Am I right? Okay, that's the slope. And now what's the equation? We use the point slope. I have a point and I have a slope. So this is a point. So I'll have 1 minus 0 is 4 times x minus 1 over 4. So y equal 4x minus 1. Okay, so that will give me the equation of the line. So it means that this is a line. This here, y is 4x minus 1. Okay, now I have the y. Y is my variable. As we did before, I need the x. So I need to solve for x in terms of y. So here my x would be, y plus 1 divided by 4. Okay, and that's what give me from here all the way to here. So now my wi, when I want it, is basically twice the xi. So now I have this distance. This distance here, in terms of yi, is yi plus 1 over 4. So it's going to be equal to 2 times yi plus 1 over 2, I meant over 4. So it's going to give me a half yi plus 1, which is exactly what we got before. Okay, so another way to do this problem analytically, that sometimes it's easier, sometimes, is introduce x and y axis. The y is the way we had it, introduce an x-axis. And then you say, if I know the equation of this line, since here I know the y here, so if I know the equation of this line, I can figure out this horizontal distance. So I went ahead and found the equation of the line for x minus 1. This will give me I find x in terms of y because I want a horizontal distance. I found the x. This would give me the distance from here to here, times it by 2. This would give me my wi. Okay, so you can use either way you actually want to. Both are correct and both are used. So it will be your choice to pick what you want. Okay. Any questions before we close on this problem? So today we are going to do the following. We're going basically to close this section and do one more problem, which is very much like, in a way, it's very much like the problem we did, pumping water, but a little bit different. I mean, but the same logic will apply to it. So I will read the problem and then we do it. So lifting problem. So a cable, I read it, I know that you guys are writing it, a cable that weighs 2 pounds per foot. So this doesn't read very well. This is 2 pounds per foot. Okay, that's the cable. And of length 100 feet hangs from the top of a tall building. The question is, find the work required to lift the cable to the top of the building. So you guys read it, write it, and then I will we'll do it, we solve it. So that's the building. Now we have a cable, and the cable hangs from the top of the building. And it has a weight, 2 pounds per foot. So we're going to lift this cable. So imagine you have some kind of a pulley or something that's lifting the cable. So we're lifting it basically. And the question is, what's the work needed to lift the cable to the top of the building? So that's my cable. From here to here, it's 100 feet. And we need to lift it. What's the work done? All right. This is, in this problem, we're facing the same issue that we face in the water problem, which is the following. If I want to lift a piece at the bottom of the cable versus a piece in the top of the cable, the work needed to lift the piece here and the work needed to lift this piece are very different because they are definitely lifted by a totally different distance. Okay, so we have absolutely to account for that. So it's not like the spring or the leaking bucket where I have a specific object, one object to move. I don't have that. I have really this whole chain to move. And the force here, the distance by which this piece has to be lifted is very different than the distance by which this piece was lifted. So for this follow the reason, we're going to do exactly what we did in the previous problem. So it means we're going to divide this into chunks, into little pieces, and lift every piece by itself, or find the work needed to lift every piece by itself. So we're going to use the same kind of logic because really we have the same situation. So basically, I'm going to divide it into chunk. So that's really the picture of my mind. Chunk, chunk, divided. That's really what that's how I'm thinking about this. Bunch of chunk. I'm going to find the work to lift this, plus the work, plus the work, plus the work, plus the work. So I'm going to find the work to lift every chunk by itself. And then I'm going to add all those elements of work. So to do that, we introduce a 0. So I can introduce my 0 here. And I can orient myself this way. Okay, and then we're going to find the work done on each layer. So we're going to divide the cable into little pieces. Of length delta y. Delta y. So we're going to divide it into pieces of length delta y. So the picture in my mind here is that, so that's really, I'm going to repeat this picture without those. So that's my cable. That's my 0, and that's my y. And I'm going to divide it into chunk like this. That's a typical chunk. So that's my chunk here. Okay, and I'm going to focus on one of them, which is YI unit above the base. And I'm going to see if I want to lift this little chunk here, YI unit. What's the work done on this little chunk right there? So divide cable into little pieces of delta Y. And let's focus on the work done on a single piece. That is YI unit above 0. Is what's the work? It's the distance by which this piece is going to be lifted times the force by which it's lifted, which is in this particular problem, the weight of the piece. Okay. So exactly in a way, the same kind of approach. We divide this into pieces and we focus on each piece. And we say, okay, what's the work needed to lift each piece by itself? Now, I'm going to take every part of it and compute. Distance, weight. So the distance. By what distance is every piece going to be lifted by? Back to you.
100 minus y.
Yeah, the distance is here because this is going to be lifted all the way up to here. Now, what's the weight of every piece? Because this piece now, in your mind, you're lifting only that. That's what you're lifting. In your mind, you're lifting only this. You're not lifting the whole picture. That's what I am lifting. This is the chunk I'm lifting. This piece I'm lifting. This piece. That's the rope right here. That's the one I'm lifting. What's the weight of this little piece? I take you back to the problem so you can put the ideas together. So this cable has, of course, it's not thin air. So this cable weighs 2 pounds per foot. So what's the weight of a little piece? Well, 2 pounds per foot, this should remind you basically the idea of a density, because density is weight per unit of length or unit of area or unit of volume. That's really what the density is. So what is the weight of a little piece in this problem?
Would it be 100 or 20? Yeah, would it be 2 divided by y?
2 divided by y
Because that's your length.
is the length from here to here.
Mm,
2 pounds. 2 pounds is not, it's the weight per foot. It's the weight per foot. It means what's the weight of half a foot? What's the weight of 1/4? What's the weight of 1/3? It's not it's just the weight per foot. It's a density. Yeah, depends on how many unit, right? How many unit?
100. So would it be 2 over 100? Does that make sense?
No. I mean, I don't know what 2 over 100 will give you. I want you to understand this. What does it mean 2 pounds per foot? What does this mean? Let's
Wait,
understand.
every foot there's 2 pounds.
Right. Every foot weighs 2 pounds.
Oh, would it be 2 times 100?
2 times 100 will give you the weight of what? Everyone.
The weight of the entire chain.
Right. Is this what I'm interested in?
Oh, no.
No, I'm not interested in the weight of the whole chain. What am I interested in? Everyone. The weight of what? What is it I am lifting in this problem?
You just want the weight of the individual piece.
Right, exactly. The individual piece. That's the piece I am lifting. Back to you. What's going to be the weight of this little piece? Let us play a game because I don't want to give up.
Is it 2 times delta y?
Yeah, exactly. It's 2 times delta y. Why it is 2 times delta y? So let us play a little bit of a stupid, baby games. Suppose I'm lifting half a foot. Suppose delta y is a half, which is a lot. Then what will be the weight of the layer?
1.
What did you do?
You're just delta y is the length of just the piece, so you're multiplying that by 2.
Yeah, because this is how many pounds per foot. You multiply it by half, it means 1 pound. So delta y is 1/4 of a foot. What's going to be the weight of this piece? It's 2 pounds per foot. If it's 1/4, you're going to multiply this by 1/4, so it's going to give you a half of a pound. Okay, so what's going to be the weight? It's going to be the density, basically, times the length. It's going to be 2 times delta y. So it's the density, that's a pound per foot, times delta y, which is in feet. So the unit, feet and feet will cancel out. The unit is going to be a pound. Okay? So what we're interested in is, as your classmate said, is only the weight of this little piece. So what's the weight of this little piece? The weight of it is, basically, it's the density. 2 pounds per foot, that's the density. It's a linear density because this is kind of a line. So it's going to be 2 times delta y. And now we can put the idea whole together. So now the distance to work done on one piece is on one piece is going to be the distance by which one piece is going to be lifted times the weight of this little piece. So that's the distance, that's the force. So the delta y is part of the force. And now the idea is the same as before. So the total work, so the work is basically sum of the work done on each piece. So now we turn this into an integral. That's going to be 100 minus y times 2 dy. And the integral will go from 0 to 100 because we want to lift the whole cable. And now the rest is 2 is a constant. Integral from 0 to 100 of 100 minus y dy. And then the rest is simple. It's 100y minus a half y squared evaluated between 0 and 100. And the unit, once you compute that, will be pound-foot. So again, the weight, usually the weight is density basically times the length, because this is pound per foot. So it's the density times the length. My length here is my delta y. Now let us say I'm going to add one little thing to this problem. So suppose in the previous example, we do the following. We have the cable, and at the end of the cable, we put like a bucket of, let us say, weight 20 pounds. And the question is, what's the work done on lifting the bucket and the cable? So I will write this down clearly, and then we look at it. But I'm slowing down, so all of you, if you're writing, you can do that. Are you guys done?
Yeah.
Yes, okay. So now let me add a little question to that. So let us assume the following. Assume that we attach a 20-pound bucket to the end of the cable in the previous example. Find the work required to lift the chain and the bucket, or I meant the cable and the bucket. So what is the problem here? The problem here is that exactly like the previous problem. So we have the top of the building here, and we have my cable, and right here at the end of it, we have this bucket, and this bucket weighs 20 pounds. And this cable is the same. So it's 100 feet, and it's 2 pounds per foot. That's basically the density. You can think of it. That's not you can think of it. That's really a density. That's the density of the cable. So the cable is 2 pounds per foot. So how do we handle this type of problem? How are we going to think about it?
Seems like the only thing that would change would be the weight. So we would take 2 delta y plus the constant of the bucket, 20 pounds.
Exactly. That's one way we can do it. Perfect way. The only thing is changed is the weight. Another way to do it, so you're perfectly correct. Or another way to do it, which is probably something a little bit easier, is to think of it like the work to lift the chain plus the work to lift the bucket. So we can also separate them into two. So because when we divide this into chunk, and you can think of this as one chunk by itself, that's going to be lifted by 100 foot. So either, as your classmate said, so what your classmate suggested, which is absolutely perfect, is the following. He told me at this stage, when you take the weight of the piece, you tag on to it the weight of the bucket. Okay, so here, instead of the 2 delta y, you have to tag on the weight of the bucket. But another way to do it, which is I think is a bit easier, is to split them. You said the work is work done on the chain, on the cable, separately, plus the work to lift the bucket. Okay. This will really simplify the problem tremendously. The bucket is easy because you can think of the bucket as one solid object with a constant force that's being lifted. So we don't have a lot of issue. So the work on to lift the bucket is equal to, this is it's a constant force because there is one object that I am moving, nothing else, is the weight of the bucket times how long the distance you're going to lift the bucket by. So that's the work done on the bucket, which is pound-foot. The work done on the cable is like what we did before. So work done on the cable is from the previous example, the integral from 0 to 100 of 2 times, and we had 2y 2 times. It was 2 delta y, and this was 100 minus y. So 2 times 100 minus y dy. So the total work is going to be?
I got 10,000 for on the cable.
Oh, thank you very much. 10,000. I love it when you guys do this. So this is going to be equal to 2,000 lift bucket plus 10,000 lift cable. Okay, I meant 10,000. Okay, so it's going to give me finally 12,000 pound-foot. Okay, so the easiest way to do this problem is actually separate them into, you think of a bucket, one object, you lift it, how much work you need. The cable, you have to divide it into tiny little pieces and think about the work done on each piece by lifting it. End of the problem. Okay, with this, we finish the application for now. And what we're doing next, so you guys will have, of course, a problem for tomorrow. And what we're heading toward now is basically the second part of the course, which is integration. So what we're going to do now is we're going to go back to the method of integration. And this will take me to chapter 9, I think, no, 8 in your book. Okay, so don't worry about 7. 8 in the book, or the method of integration. So let me tell you what you know and a lot of things we don't know. The 2 things we know about integration are, first, basic antiderivative, integral of x squared, x cubed, 1 over square root of x. So we know some basic, and we know substitution. That's the part that I started with. So suppose we have the integral, I don't know, I can make up anything, cosine x, sine cube x. No, actually, it's much easier than that. So substitution. A typical problem was x times x squared plus 1 to the power 4 dx. That's a typical substitution problem. And in this problem, the substitution is very clear. We set u to be the x squared plus 1. The du is the 2x dx. And then we proceed this. I isolate that, which gives me u4 du. So that's what we studied. That's what I tested you on. I meant 1 over u10, u to the 5 plus c, which will give me that. Plus 1. Substitution. Now, if I do a tiny change, sometimes the substitution, suppose I give you x times x plus 1 to the power 4 dx. Okay. All right. I'm just going to give you a hint how to do that because I assigned 3 problems along those lines and I let you go. Now, is this like the previous problem?
No, because when you take the derivative of x plus 1, you're left with 1. And you can't multiply back into the integral.
Absolutely. So definitely is different. But this problem can be also done by substitution, and which is weird, but we can do it. So it's the hardest, not hardest substitution, but a different kind of substitution. So how can we do substitution in this problem? This is problematic for us, unless you expand it. So see how it works. It's a bit tricky. It's kind of fun. Again, we're going to put u equal x plus 1. The du is the dx. But then, of course, everybody with you should be screaming, why can't she do that? There is no, what's she going to do dx? And the trick is we actually can substitute x in terms of u, because it's a very simple scenario. What do I mean by that? If u is x plus 1, x is u minus 1. So I can substitute that, and it's going to become x will turn into u minus 1. And this will turn, so I've never done anything like that before, but I don't think it's very hard. And now the problem is simplified. That's going to give me u to the power 5 minus u to the 4d. And then this would give me 1 over 6, u6 minus 1 over 5, u5 plus c, which will finally give me that. So sometimes substitution can be done in a little bit more complex way than the way we've done it, even though the way we've done it is the essential way. That's the most important way. This is sometimes we can do it to fit some scenarios, and that's going to give me to the power 5 plus c. Okay, so that's a different kind of substitution, and I assigned 3 problems that has to deal with this kind of substitution. So before I'm out of time, I'm just gonna ask you a question. So for example, suppose I have this type of problem, okay? And I wanna find the antiderivative using this new kind of substitution I had, because there is nothing here that works. I mean, it's x squared over x minus 1. It's absolutely no idea how this would work. So this is one way you can do that is, put u to be the denominator because it's bugging me. Du will be the dx. And then this will turn my integral into the following. X minus 1 is my u. Dx is my du. But then I'm going to put the x squared. I'm going to solve for x in terms of u. X would be u plus 1. And then this would become u plus 1 squared. I usually take the phone away from my room. Today I forgot. Then once we do that, the problem will become simple. Du. Once I divide by u, it will be u plus 2 plus 1 over u. And the rest is simple. So this is a kind of substitution, was slightly different than what we did, but it works in some problems where regular substitution is going to fail. Okay. So for tomorrow, I assigned 3 problems along those lines. Please do them. And 1 problem along the cable. So it will not be a hard homework. And we're going to move on to chapter 8 tomorrow, and we're going to start integration. So for the next 3 weeks, we will be doing nothing but integrating. Okay. Any questions?
Yeah, does this only work if du equals dx, or can it also work if that's different?
It works as if it's a little bit different. I will try to make up problems for you to, so you can work with that. Once we develop more integration techniques, okay, I will go back and give you more interesting problem for that.
All right, thanks.
Yeah. Any other questions? All right, see you tomorrow, guys. Bye-bye, guys.